Hey everyone, so we're looking at section 6.8 today, and this is going to be the last section we will be talking about in chapter 6. And here we're actually talking about the graphs of polar equations. So of course we have seen graphs that were sketched in our rectangular coordinate system before. Now, here, basically the idea was when you were graphing your rectangular coordinate system graphs, we were using the basic point plotting method, right? Which means you find your x and y coordinates, you find as many points as you think you need to get a good graph for your equation, and basically that's your like I said, that's your basic method of graphing. But then you can also use aids, sketching aids such as symmetry, your x and y intercepts, maybe the asymptotes, periods, and shifts to basically, like they're saying, further investigate the nature of graphs. And of course, we saw this even before when we were graphing the trigonometric functions, right? We talked about periods and shifts, we talked about amplitude, and then of course, if symmetry, intercepts, asymptotes, any of those can be helpful, we want to use those as well. So, like I said, in this section, we're going to be talking about the graphs, the curve sketching in the polar coordinate system. And basically, we will try to see what sketching aids we have, what kind of tools can we use to come up with decent graphs for our polar equations over here. And of course, we are also going to start by looking at point plotting. So our first example here is asking us to sketch the graph of the polar equation r equals 4 times sine of theta. So of course we know sine function is periodic, right? And so you can basically, they are saying, obtain a full range of your r values over here by looking at different values of theta from the interval of 0 to 2 pi, including the endpoints. So if you just look at all of these theta angles that we have over here, basically those are the angles that you would find in your unit circle. So we're just using all of those angle values here, going from 0 all the way to 2 pi, and then finding our r value by basically substituting for theta in our given equation. And once you have these points, your table completed, basically, you have all these points that you need, you can basically start plotting these points on your polar coordinate system, right? And they are saying basically once you are done graphing, it looks like your graph is going to be a circle that has a radius of 2 units, and the center is going to fall at the point 0, 2. So basically right here is the center of our graph, and then you can see it has a radius of 2. So let's go ahead and take a look at our equation over here. They're asking us to graph the polar equation r equals 6 times cosine of theta. So let's see what this comes out to be. Okay, so before we look at the graph, I just wanted you to know this is kind of what our blank polar coordinate system will look like, and this is what we're going to use to try and come up with the graphs of our equations over here. So let's go ahead and take a look at this first one here. So of course we are also going to use the concept of point plotting. So again, you should know, since this is r equals 6 times cosine theta, the cosine function is also periodic. So basically we can again use theta in the interval of 0 to 2 pi. Okay, that will give us a full range of values for our r value. So let's go ahead and do a little table over here. And you know what, I think I'm going to do this down here. So let's do theta values on the top, and let's do r values on the bottom. So we'll start with our angle 0. Now basically the idea is your r function is r equals 6 times cosine theta, right? This is our equation. So when we are given 0 as our angle, you're basically looking at r equals 6 times cosine of 0. So again, keep this unit circle handy. So cosine of angle 0 is going to be positive 1. So this will end up giving us 6 times 1, which will give us an R value of 6. So this would be the ordered pair 6 and angle 0, right? So this is how you would go about finding all of these values. And then, like I said, you can go through all your normal theta values from your unit circle. Okay, so let me show you another calculation over here. So if we did R equals 6 times cosine, our second angle is pi over 6. So for pi over 6, our cosine value is square root of 3 over 2. So that's going to be 6 times square root of 3 over 2. Of course, you can see 2 will cancel out into 6 3 times, so you will end up getting the answer 3 square root of 3 for your R value. So this ordered pair would be 3. And that should not be a comma there. This will be 3 square root of 3 for the angle of pi over 6, right? So this guy is 3 square root of 3. So basically we need to complete the table and go all the way to 2 pi to get all our values over here. Alright, so this is what your completed table ends up looking like. Now, of course, try to use as many of these points as you comfortably can to try and come up with a good shape of your graph over here. So let's see what happens when we put these together. So you know what? I think we're actually going to need another circle in here to get us to that value of 6, because we have 0, 6, 2 pi, and 6. So let's go ahead and create another circle for this guy. Okay, so let's see. At the ordered pair 0, 6, you would be looking at a point over here. Then let's see, our next good point was at pi thirds and 3. So pi thirds and 3 would be a point over here. At pi halves, we have 0. So I'm looking at all of these points right now that have a nice value, right? Instead of going for those 3 square root of 3 and 3 square root of 2 kind of numbers. So at pi halves, we have 2. Let's see, at 2 pi over 3, we are at negative 3. So that would be, let's see, 2 pi over 3 and negative 3. No, I put it on the 4. This should be negative 3. There we go. And then let's see what's our next good point. Pi is at negative 6. So for pi at negative 6, okay, 4 pi over 3 at negative 3, so 4 pi over 3 at negative 3. See, 4 pi over 3 at negative 3 will actually take us back to this point. 3 pi halves is at 0. 5 pi over 3 is at 3, which will be this point again. And then 2 pi is at 6. Okay, so those are not going to be enough points, which we will need to do these approximations here. So let's look at what this guy at pi over 4 is going to be approximately equal to. So that is 3 times square root of 2. And this is approximately 4.2 at pi halves. 4.2 would be somewhere over here. And then let's see, 3 pi over 4 would also be at negative So this guy would be negative 4.2. And can we find another point? Let's see, at pi over 6, we have 3 square root of 3. So this guy here will be approximately 5.2. So let's see, pi over 6, 5.2, so somewhere over here. And this guy again would be approximately negative 5.2 at 5 pi over 6. So approximately negative 5 over 2. So hopefully this will give you a little bit of an idea. And you know what happens is after you get to the angle pi, all of these are actually going to be repetitions because you are actually going to be going over those same points twice. So this guy should actually come out to be, I guess that's not going to work, so I'm going to try and do this freehand, but it's probably not going to look pretty. Oh, and this point is in the wrong place. Okay, so this will end up looking something like this. It's going to be a little bit off, but basically you should get an idea that this is going to look like a circle if you draw it properly. So basically this is going to be a circle with the center at 3 0 and a radius of unit 3. Okay, so it may take a little bit of time. Like I said, you try and want to use more points if you want to find more angles in between, and try and use those, but it should give you a general idea of what this looks like. So basically the graph is a circle. Well, let's put it this way. The graph is a circle of radius 3 with the center at the point x comma y, which will actually be 3 comma 0. Okay. Alrighty, so this should kind of give you an idea of how we went about doing this, but let's talk about some other aids which may actually come in handy with this. Now, the other thing you could have actually done is, you know how we used the rectangular form by converting our polar equation into our rectangular equation and then sketching the graph. So you could have actually done that also if you wanted, which in this case would have ended up being, let me just show you that really quickly. So you could have taken your original equation r equals 6 times cosine theta. We would have multiplied both sides by r. So you would have ended up with r squared on the left side, 6r cosine theta on the right side. Now you can substitute for r squared with x squared plus y squared. And then you could have substituted for r cosine of theta with x, and you would have ended up with 6 times x over here on the right hand side. And then of course bring all the terms on the same side, so we would go ahead and subtract the 6x. You would end up getting x squared minus 6x plus y squared equals 0. And then we would have done completing the square, which would have been taking the number 6, dividing it by 2, and taking a square on that. 6 divided by 2 is 3. 3 squared is 9. And then we would have added x squared minus 6x with 9, keeping the y square as it is, and then 0 plus 9 on the right hand side. We would factor this term over here, which would factor into x minus 3 squared plus y squared equals 9, and you can see this will give us the center of our circle at positive 3 and 0, and our radius would have come out to be square root of 9, which would of course give us a radius of 3, and that's the exact same thing we have over here, a circle centered at 3, 0 with a radius of 3. So that's another way that you can come up with these graphs, is by converting them from a polar equation to a rectangular form of the equation. So that's kind of what they're talking about here, is converting this and then sketching your graph. Of course, you can use a graphing calculator set in polar mode, or you can also use your graphing utility set to the parametric mode and using that to help you come up with the graph of these functions. Alrighty, now let's talk about some other aids over here. So we're looking at how to find the symmetry, how to find the zeros and the maximum values for the R value. So they are saying, if you look at example 1, that theta increases from 0 to 2 pi, your graph is traced twice. So basically, if you use the values from 0 to pi, you already get that one complete rotation of your circle, but if you go back and use the remaining values, you will go ahead and actually trace this graph twice, and that's the same thing that will happen in the example we did. And they are saying, moreover, make a note of the symmetry with respect to the line pi half. So basically they are saying, if we fold our graph along this line here, the two halves of our graph will coincide, and you should actually notice that in this function also we have symmetry, but it is not with respect to the line pi halves. Your symmetry is actually in respect with the line, the polar axis over here, which is this line right over here. So if I fold my graph along that line, you will see my two halves, the upper and the lower semicircle, will coincide. So you do have symmetry as part of these functions. Okay, so they're saying, had you known about the symmetry in the retracting ahead of time, you could have used fewer points to graph your function. So let's look at 3 different types of symmetry over here. So you have the symmetry with respect to the line pi over 2. So that's of course going to be this line over here. Symmetry with respect to the polar axis, which will be this line over here. And then symmetry with respect to the pole. Now remember, the pole is basically the origin. So if you take the distance of this line from the origin, it's going to have the same distance if you go in the opposite direction from there. So symmetry with respect to the pole. Now, how do we figure out what kind of symmetry do we have? So this is what we have to do, is you take your original polar equation, then to find out if it's symmetric or not, you take your original R and theta values and replace them with either R and theta minus pi, or negative R and negative theta. And if you get the same original equation, if you get an equivalent equation, that means we have symmetry with respect to the line pi over 2. Okay, if you take your original R and theta and replace it with positive R minus theta, or with negative R pi minus theta, then, and you get the equivalent equation as your original, you can say we have symmetry with respect to the polar axis. And if we replace the original R and theta with R pi plus theta or negative R theta, and you get the equivalent as the original, you can say your symmetry is with respect to the pole or the origin here. So you would kind of have to do this check, and sometimes you may actually have to do all 3 checks for symmetry to see if our function can have just one of these, 2 of these, or all 3 of these in the same function, and it is possible. So they're asking us to use the symmetry to sketch the graph of r equals 3 plus 2 times cosine theta. So here we are taking the original r and theta and replacing it with r minus theta. So of course you will see the r value stays the same, but the theta becomes negative. So if you take 3 plus 2 times cosine of negative theta, you actually get the same thing as your original equation, and that's because the cosine function is an even function. And so since it is an even function, your cosine of negative theta just ends up becoming cosine of theta. So in this case, we use r and negative theta. So this was the second case over here. And since we came back to the original equation, we can say we have symmetry with respect to the polar axis. So with respect to the polar axis is going to be the second, or the graph in the middle over here. That's kind of the thing you are looking at. Okay, so again, we will go ahead and calculate our points, and you will see we only went from 0 to pi over here because, of course, you will be tracing the graph over again if you did the other points, but you can go all the way to 2 pi. So using the points in here and using this idea of our polar axis symmetry, we will actually end up getting a graph like this. So you will see we only use the points from 0 to pi, and then the fact that it was going to be symmetric along the polar axis, these points are basically reflections of the top half, and that's how we come up with this graph over here. And this type of a shape, or this type of a graph, is what we call as a Limocon. That's one of the pronunciations. I've also heard this being called as Limaçon. So either Limocon or Limaçon, whichever one you prefer. I think I'm going to go with Limocon because that seemed to be a more popular pronunciation. But that's what this shape will come out looking like. And you know what's happening is if you just had 2 cosine of theta, then you would have had a circle. But because now we are adding that 3 in the front, that's what gives it this little unusual shape of the Limocon. So let's see how symmetry will work with our example over here. We are given r equals 3 plus 2 times sine of theta. So let's go ahead and take a look at this guy. So the first thing we want to do is figure out what kind of symmetry our function has. So we are going to replace our original r and theta with, we'll just start with the first one, replace it with r and pi minus theta. Okay, so we are given r equals 3 plus 2 times sine theta. We're keeping the r value the same, but we're replacing theta with pi minus theta. So again, r equals 3 plus 2 times sine of pi minus theta. Now sine of pi minus theta, we are actually going to have to use the sum and difference formulas, which is what we had seen back in, I think it was chapter 2. Okay, section 2.4. Okay, I have written this down actually. So this was in section 2.4 where you will find your sum and difference formula. So let me just go ahead and write that down. Oh, I guess I'll write it down here. The sum and difference formula, when it's sine of u minus v, is going to be sine of u cosine of v. I don't think I'm going to have enough space. Oh well, I think I'm just going to write it here. Sine of u minus v is going to be sine of u cosine of v minus cosine of u sine of v. So when you translate that for this equation, it will come out to be sine of pi cosine of theta minus cosine of pi sine of theta. So again, sine of pi and cosine of pi. we are looking at the angle pi over here, so cosine is -1 and sine is 0. So that will give us 0 times cosine theta minus, this is -1 times sine of theta. So that will then become 0 times cosine of theta will become 0. Over here, negative and negative will become positive, so you'll end up with positive sine of theta. And of course, just cleaning it all up, we get 3 plus 2, 0 plus sine of theta will be sine of theta, and you will see that we actually, in fact, go back to the original equation over here. And remember, we used our theta value was replaced with pi minus theta. So just to show you, when you replace it with r and pi minus theta, we're looking at case 1 over here, and this is the replacement we did. So that tells us we have symmetry with respect to line of theta equals pi halves. Okay, so this is going to be symmetric with respect to the line theta equals pi half. So basically, with respect to that 90-degree angle line that you have, that's where you're going to see the symmetry. Now you can check it for the others, and you should do that. I've already done the checking and it does not work, but this is the only symmetry it will have. But of course, just by looking at the graph, we don't know that, so we always want to try and check with all 3 of the tests and make sure there are not multiple symmetries that you are seeing here. Okay, so now that we know the symmetry, let's go ahead and find our points over here. So again, we'll do our little theta and r values table over here and see what are the different measurements we get for r at the different angles. Okay, so just to show you what this table would end up looking like, if I'm using my angle as 0, then that would be 3 plus 2 times sine of 0, again, is going to be 0. Okay, so that would end up giving you 3 plus 2 times 0 is 3 plus 0, or basically you get the answer 3. If you try this with the angle at pi over 6, well, sine of pi over 6 is going to be 1/2. So that's 2 times 1/2, which means the 2 and 2 will cancel each other out. You're left with 3 plus 1, which will give you the value of 4. So in that same fashion, you will go ahead and complete this table here, okay? Okay, so here's our completed table, and I've actually gone all the way to 2 pi, but again, find the points that you think are going to work for you the best, and then let's go ahead and plot them. So let's start with 0, 3. So that is going to be at the angle 0 and 3. Then let's see, pi 6 is at 4. So that would be here. Pi halves is at 5. So pi halves is at 5. Let's see, 5 pi over 6 is at 4. 5 pi over 6 is at 4. Pi is at 3. So pi is going to be at 1, 2, 3 over here. Okay, 7 pi over 6 is at 2. 7 pi over 6 is at 2. Okay, 3 pi over 2 is at 1. So that's this point right over here. And what else do I got? 11 pi over 6 is at 2. So there. And let's see, back at 2 pi, we come a full circle, and then you can kind of use the other points to see where exactly you are going to be. So let's do the 45-degree angles over here. So that's 3 plus square root of 2. So 3 plus square root of 2 is approximately 4.4. So that's going to be about 4.4, so somewhere over there. Let's see, do we have another right here? 3 plus square root of 2, which will also be approximately 4.4, and that's at 3 pi over 4. So about 4.4 over here, so a point right there. Let's see, at 5 pi over 4, we have 3 minus square root of 2, so this would be approximately 1.6. So 5 pi over 4 is at 1.6. So somewhere over here. And we've got another one of these at 7 pi over 4, which is approximately at 1.6 again. So 7 pi over 4 at 1.6, somewhere over here. So hopefully this should give you enough to come up with a general shape for your graph. And let's see if I can give it a nice, good, decent shape over here. Okay, so there you go, something like this. And of course you want to try and draw the best smooth curve that you can, and if you need to get more points in there, you can try and get more points in there. This should be somewhere like this. Now this shape of our graph that we have here is what we call as a dimpled Limocon. And the reason it's called a dimpled Limocon is because if you look at this equation over here, we have r equals a plus b sine of theta, and the dimpling happens when this is true. If you have the value of 2b greater than the value of a greater than the value of b. So basically for us, the 2b value is 2, greater than a is 3, greater than b is 2, and of course you will see 2 times 2 is 4, and 4 is greater than 3, and 3 is greater than 2, and this is your a and b values. When this is true, that's when you have a dimpled Limocon. Okay, so that's what this shape of your graph is called, but this is how we would use symmetry. And basically your symmetry was with respect to the line theta equals pi half. So you can see if we fold our graph along this line over here, those two halves are going to be equal, they will coincide. So this is how you would come up with the graph for this equation over here. Okay, alrighty. Oops. No. There we go. Okay, so they're telling us for our example 2 over here, it uses the property of the function that cosine is even. And of course you saw that right over here when we plugged in negative theta for our original theta value. Now you can actually go back to section 1.2 as it says here to look at the definitions, but cosine function is even because when you put a negative theta value, you still get the same value as cosine of positive theta. And of course your sine function is odd because when you put a negative value inside of your sine function for the theta, it basically ends up making the whole sine value a negative value. Okay, we've of course looked at many different examples with that, so if you want to go back and review, you can do that. Okay, so we're saying these tests that we just talked about are sufficient to guarantee symmetry, but a graph may have symmetry even though its equation does not satisfy the test. So this is an interesting thing over here, that you may still have symmetry in your graphs even though these tests tell you otherwise. So they are talking about if you have this graph over here, which is r equals theta plus 2 pi, it's basically, you can see, has symmetry with respect to the line theta equals pi half. So if you were to fold it along this vertical line, the two halves would coincide. They are saying, and yet the corresponding test fails to reveal this property. Of course, neither of the replacements will give you an equivalent equation, and you can see they are showing you the replacements over here with the original r and theta values in our function, and you will see when we get the new equation, they are not similar to the equation that you started out with, which is theta plus 2 pi. So these equations do not come out to be the same. So sometimes those tests of symmetry can yield these kind of results for you. So just kind of keep that in mind, okay? So the examples that we saw in examples 1 and 2, the equations that we saw in examples 1 and 2, basically you can see this function here, r equals 4 times sine of theta, is basically a function of the sine function, sine of theta. And the second example here is 3 plus 2 times cosine of theta is the function of this form, where r equals g of cosine of theta. So these graphs both had symmetry, and the way this symmetry you can actually look for it is if you have a graph of a function for r which is equal to a function of sine of theta. So if it's using sine of theta, it will have symmetry with respect to the line theta equals pi half. So that's going to be with respect to that vertical line. When you have a graph of the function r equals, again, it's a function of cosine of theta, g of cosine of theta, you will have symmetry with respect to the polar axis, which is going to be that horizontal axis. So just keep in mind, if you have an equation which is using sine of theta as its function, you will have symmetry with respect to theta equals pi over 2, the vertical line. And if you have a function which is r equals to a function of cosine of theta, you will have symmetry with respect to the polar axis, which will be that horizontal axis over here, okay? Now, the two other aids we want to talk about, which will help us in sketching these graphs, is going to be involving the values of theta, and based on those values of theta, what kind of r values we are getting, so we can figure out where our r function, and that's absolute value of r, is going to be maximum. And also, with the given theta values, we can figure out where the r values are going to be 0. So in our example 1, where this function was r equals 4 times sine of theta, they are saying the maximum value of r is going to be absolute value of r equals 4. And this happens when the angle is pi halves, and the value of r is going to be 0 when theta is 0. So let's verify that really quickly over here. So you can see we had the maximum value for r at positive 4 or negative 4, because we are talking about the absolute value of r being 4, and that happens at the angles of 3 pi halves and pi halves. If you only want to look at it from 0 to pi halves, then this will happen at theta of pi halves between 0 and pi. And then for when the r value is equal to 0, you will see they are equal to 0 at angle 0, equal to 0 at angle pi, equal to 0 at 2 pi. So you can basically say they will be equal to 0 when theta is 0 or theta is pi, or when theta is 2 pi. So that's kind of what we're talking about. You can figure out where your R values are going to be at a maximum point at, and where your R values are going to be at a 0. And that can also help us with the graphing of these polar equations. So let's look at this example here. We are given R equals 1 minus 2 times cosine of theta. So let's start with symmetry. Now, since this is a cosine function, you will have symmetry at the polar axis. Your maximum value of R, again, look at this table here going from 0 to pi. You will see my maximum value is going to be right here at the number 3, which happens at angle pi. And then I have the value of 0 for my R value when my angle is pi over 3. So that way you have your maximum value, you have your 0, and so you will notice at the value of pi, this is where we have our maximum point at pi as my angle, and R value is 3. And then you can see my 0 is happening at pi over 3, which is going to be this point actually right at the origin, as you see. And you would actually have a 0 over here also, but this we would need to go further out to see that. But yeah, this is where you will have your R value as 0, and this is where you will have your R value at maximum, and this ordered pair is actually coming from angle 0 being at -1. Okay, so all of these help you figure out what the shape of your graph is also going to be. And then since we know we have symmetry with respect to the polar axis, you can see the top half will coincide with the bottom half. Okay, now the other thing that's going to happen is you see all of these negative values that we have in here. Those negative R values are actually what's causing for that small little inner loop that we have on our function. So that happens when you have those negative R values in your function values. And of course, this is still a Limocon for our graph. Okay, so let's see what our example ends up looking like. We are asked to graph the function R equals 1 plus 2 times sine of theta. So let's go ahead and take a look at this guy. So let's start by talking about symmetry first. So we have a sine function, and since this is a sine function, we will have symmetry with respect to the line theta equals pi halves. And you know, I would still suggest using those 3 tests for symmetry to help you out in this case. Okay, so we've got our symmetry, which means we're talking about symmetry with respect to that 90-degree angle line. Now let's find out where the maximum value of our absolute value of R is going to be at, and where the 0 for the value of R is going to be at. So let's go ahead and create our table over here, and again go all the way from 0 to pi or 0 to 2 pi, whatever you are comfortable with. Okay, so again, if we start with angle 0, our equation is R equals 1 plus 2 times sine of theta, so that will be 1 plus 2 times sine of 0. And of course, again, you should know sine of 0 is 0. So you end up getting 1 plus 0, which of course will give you 1. So we have 1 over here, and of course, repeat that process for your other theta angle values. Alright, so here we have our table. Now we need to find where we have our maximum values at, and let's see, we have 1, 2, 3, and yep, that seems to be the maximum value. So that is happening. A maximum value of absolute value of r would be r equals 3 when our angle is pi halves. And then let's see, where do we have our zeros at? And it looks like we have our 0 at 7 pi over 6, and we also have a 0 at 11 pi over 6. So we would say r equals 0 when theta equals 7 pi over 6 and at 11 pi over 6. Okay, so this is what you would end up coming up with for the maximum and the zero values of r. Now, of course, we have our table. We have our symmetry with respect to the line. Theta equals pi over 2. So we can now go ahead and see what our graph is going to end up looking like. So let's see, at 0, we have the value of 1. So that's going to be right over here. At pi over 6, we have the value of 2. Pi halves, we have a value of 3. Let's see, 5 pi over 6, it's 2. Okay, and then at pi, it's 1. 7 pi over 6 is 0, which is going to be right here at the origin. At 3 pi halves, it's at -1, so that would actually be over here with 3 pi halves. 11 pi over 6 is at 0, again at the origin, and then at 2 pi, we are back at 1. Let's see what these angles are going to be at our 45-degree angle. So we have 1 plus square root of 2, which gives you approximately 2.4, and that will also be here, approximately 2.4. So let's see, at pi over 4, it's 2.4. So 2.4 somewhere over here, and that's also at 3 pi over 4. So 3 pi over 4 at 1, 2, 2.4, maybe somewhere over there. If you want to do pi over 3 and 2 pi over 3, that's going to be 1 plus square root of 3. So that's looking approximately at 2.7. So at pi over 3, we are at 2.7. So just a little quarter below number 3, and then at 2 pi over 3, same thing. And so maybe somewhere over here. Now this one is going to have the shape with that little inner loop on the inside. So let's see if we can get this general shape here. This will be going somewhere like this. And then you would basically making that little inner loop on the inside. Okay, so just a general shape for our graph over here. And this will be this is a Limocon which has an inner loop. Okay, there you go. So this is what your graph is going to end up looking like, and you get an Limocon with an inner loop when you have your function in the form a plus b sine of theta, and you get this when your b value is greater than a, and of course you will see our b value is 2, and 2 is greater than 1, which is our a value over here, and this is what gives us a Limocon with the inner loop. Okay, so you've got your symmetry. So again, you can see if we fold our graph along this line of pi halves, the left and the right hand side will coincide. You can see your maximum value is at r equals 3 on the theta value of pi halves, and then we have our zeros at 7 pi over 6 and at 11 pi over 6. Okay, so this is our example number 3 over here. Alrighty, so they are saying some curves can reach their zeros and maximum r values at more than 1 point. So you can actually have multiple points, as you will see here in this example 4 over here. So we are sketching the graph of r equals 2 times cosine of 3 pi. So again, being a cosine function, you're going to have symmetry with respect to the polar axis, but again, use those 3 tests of symmetry to verify you don't have more than that. Creating our table over here, you will see we have our maximum value at angle 0, maximum value at pi over 3, and zeros at pi halves and pi over 6. So you've got maximum at angle 0, pi over 3, and then they didn't go further on this table, but if you did, you would have come up with these 2 other angles also. And then your zeros are at pi over 6, pi halves, and of course 5 pi over 6 if you were to go beyond. If you actually just go ahead and take these angle measurements over here and multiply each of them by 3 to get your 3 theta, you would come up with these numbers over here. And this is just to show you the matching for the 3 theta, which is given to you in your equation, but you don't really have to do that as long as you have your values for theta, like we do here. So we've got our symmetry, we've got our maximum and a value of r and the zeros of r. So using this these aids over here, and of course the points that we have in our table, you will actually get a graph which is what we call as a rose curve, and each of those loops are basically what we call as petals. Okay, so you are basically just going from the angle of 0 to pi, 0 to pi, and you will see that ends up giving you the entire curve for your angle measurement. So this is kind of the stages. They're just breaking it down for you, showing you as we go from different angle measurements how that curves come out to be. Okay, so this is what we call, again, like I said, as the rose curve. So let's go ahead and take a look at our example over here. We are given r equals 2 times sine of 3 theta. Okay, so this guy over here, let's start by talking symmetry again. So this is a sine function, so we know our symmetry again is going to be with respect to the line theta equals pi half. So again, our 90-degree angle line. Now let's figure out where our maximum values of r are going to be at, and that's absolute value of r, and then where the zeros of our r values are also going to be at. So again, we're going to go ahead and create our table. Okay, again, just to show you our first calculation, the equation is r equals 2 times sine of 3 theta. So if our angle is 0, 3 times 0 will of course become 0. And again, you should remember sine of 0 is 0. So 2 times 0 will end up giving you 0. Okay, if we did our next angle, which is going to be at this one. We're actually going to break it down into a little bit more smaller angles. So let's do pi over 12 so we can get a good continuous curve for our petals over here. So this is 2 times sine of 3 times pi over 12 as our theta value. So you can reduce this. 3 goes into 12 4 times, and you will end up getting sine of pi over 4, and 2 times sine of pi over 4 is actually going to be square root of 2 over 2. So square root of 2 over 2, again, the 2 on the top can cancel out the 2 on the bottom, leaving you behind with an r value of square root of 2. So again, go ahead and calculate those angles, and this time we're just going to go all the way to pi. Okay, so let's go ahead and see what those values come out to be. Okay, so we have all our points now going from angle 0 to pi. So let's talk about the zeros. We have 0 over here, 0 over here, 0 over here, and 0 over here. So that's going to be r equals 0 when our angle is going to be 0, pi over 3, let's see, 2 pi over 3, and at pi. Now let's talk about the maximum values, and it looks like it's going to be at 2, negative 2, and positive 2. So that's going to be our absolute value of r equals 2 when our theta is going to be pi over 6, pi over 2, and what else? Pi over 2, and 5 pi over 6. Okay, so that's where we'll have our maximum and our, you can think of it as minimum at the negative 2, but we're just looking at this in terms of absolute value and our zeros. And then of course we have symmetry with respect to that line pi over 2. So let's go ahead and graph these. So at 0, we're actually at 0. At pi over 6, we are at 2. Pi over 3, we are actually back at 0. Pi halves is negative 2, so that will be going down here. 2 pi over 3 is back at 0, and then 5 pi over 6 is at 2, and you're back at 0. So of course we're going to need to do these intermediate ones. So let's do the 45-degree angle. Square root of 2, of course, is approximately 1.4. So this would be approximately negative 1.4, approximately 1.4, approximately negative 1.4, and approximately 1.4. So I'm going to do the pi over 4, which is at approximately 1.4. So approximately 1.4 would be maybe somewhere over here. Let's see, we can do 3 pi over 4. So 3 pi over 4 at 1.4 would be somewhere over here. Now if you did the pi over 12, that would actually be halfway between here. So you can kind of, if you can, just do a little point here for the divided by 12 measurements. Pi over 12, 5 pi over 12, 7 pi over 12, and those kind of numbers. And then these guys here would be 1.4 and 1.4. So you would kind of have to play around with some points to get this, but this is what, remember, this is that rose curve. And end up looking something like this. Okay, so just something like this. It will end up being our graph over here. So remember, this is a rose curve. Okay, and the trick behind the rose curve functions is your function is going to be in the form a times sine of n theta, because we have that 3 on our function, where your n value has to be at least a 2, or it can be greater than 2. And the basic rule of thumb is, if n is an odd number, you will have n number of petals. So you can see, since this was a 3, we have 3 petals in our rose curve. If n is an even number, then you will have 2 times n number of petals. So if your n was, let's say, 2 times theta, so that would be actually 4 petals. If your n was 4, then you would have 8 petals. So when it's odd, it's the same number of petals, but when it's even, you have double the petals. Okay, so just a simple rule of thumb to remember for these rose curves over here. And again, you can see the graphing process is pretty similar to the other functions we have seen, but of course, based on what kind of function you have, you get a different graph. Alrighty, so let's take a look at some other important types of graphs that we have here. So they are saying some important types of graphs have equations that are going to be actually simpler in the polar form than they might be in the rectangular form. Think about a circle that has this equation in the polar equation of r equals 4 times sine of theta, which is the first example we saw. If we converted that into our rectangular equation, it came out to be x squared plus y minus 2 squared equals 4, which would of course give you a center of 0, 2 and a radius of r equals 2, and then your, of course, polar equation for that is 4 times sine of theta. So they are saying for a lot of these types of graphs, it would be easier if you had the simpler polar equation instead of a rectangular equation, basically. So we've seen a couple different Limacons over here. So remember, Limacons are going to be of this form: a plus or minus b cosine of theta, or r equals a plus or minus b sine of theta. Both a and b have to be positive values over here. And then depending on this guy here is the relationship, but I usually look at it as a being less than b or b being greater than a. You will have a Limacon with an inner loop. If your a value is actually equal to your b value, you will have this heart shape or cardioid shape of a graph. The dimpled limocon, we actually looked at this, and this is where it's going to be b is less than a is less than 2b, or basically you can think of it as 2b being greater than a being greater than b. And then you can have a convex limacon when you have a when a is greater than or equal to 2 times b. Okay, so different types of limacons depending on what kind of relationship we have between the a and b terms. We looked at rose curves. So remember, if you have n as your odd number, you have n number of petals. If n is even, you will have 2 times n number of petals, and of course n has to be a minimum of 2 or greater than 2. So you can see here our n value is 3, so we have 3 petals. Here your n value is 4, so you actually have 8 petals. N value is 5, so you have 5 petals. N value is 2, so you have 4 petals. So these would be the different forms of your rose curves. Of course, we can have circles, and we have talked about circles in example 1. So here you have a circle when this is a times cosine of theta. You have a circle when you have a times sine of theta. And then you have what we call as the Lemniscate shape, which is basically like a figure 8, or think about it as your infinity symbols. These are all called as Lemniscates. So you can have those, and then depending on, do you have r square equals a square sine of 2 theta, you can see what that graph looks like. And then if you have r square equals a square cosine of 2 theta, you can see this is going to be more of a horizontally oriented graph over here. Okay, so just different types of polar equations and what their graphs end up looking like. So this is kind of a neat way to summarize this. And they're saying you can do the quick test for summary that we saw after example 1 over here. So you can do those little quick tests. And then they are saying especially these will be useful when graphing many of the curves that we are looking at here. They're saying, for example, Limaçons that have the form r as a function of sine of theta or r as a function of cosine of theta, we know these will be Limaçons that are either symmetric with respect to the line theta equals pi half, so they can have symmetry with respect to the polar axis. So yeah, definitely want to use symmetry, because look at all of these graphs. They have all kinds of symmetry happening here with respect to the line theta equals pi half, with respect to the polar axis, and with respect to the pole. Some of these actually have all 3 of those symmetries here. So let's take a look at this next example here, the graph of r equals 3 times cosine of 2 theta. So this equation is of course of the form right here. So you will see this is going to be our rose curve function. So, and since this is my n value is 2, this is going to be 2 times n, which means we will have 4 petals. You actually have symmetry with respect to the line theta equals pi half, the polar axis, and the pole. So all 3 symmetries are present here. Your maximum value for 3 is going to be at 0, theta values of 0, pi halves, pi, and 3 pi halves, but of course they're not showing you the complete table over here. Your 0 values for r are going to be when theta is pi over 4 and at 3 pi over 4. So using our type of curve symmetry, maximum values, and zeros for your r value, I would actually extend this table more than what they are showing you over here. And you can see we have a nice 4-petaled rose curve over here. And you should notice with respect to the line pi over 2, we have symmetry. So if I fold my left and right hand side, they would coincide. With respect to our polar axis, I also have symmetry. So if you fold along the horizontal axis, you will see the top and the bottom halves will coincide. But we also have symmetry with respect to the pole. Remember, the pole is the origin. So if you take the distance from the pole, let's say of this point over here, that will be the same distance if you took that point down here. So that distance from the pole is always going to be the same. That's how that symmetry with the pole works out to be. So that's why, I keep insisting that it's always a good practice to check symmetry for all 3 of your points. Alrighty, so let's go ahead and take a look at our sketch over here for graph r equals 3 times cosine of 3 theta. Okay, so of course we want to start out by looking at the type of curve this is going to be. So just to show you, we have the function r equals 3 times cosine of 3 theta. So you can see it's actually going to be one of these, and it's going to be the first one because our n value is 3. So it's going to end up looking something like that. So the type of our curve is going to be a rose curve with our n value equals 3. So that tells us we will have 3 petals in our curve. Let's talk about symmetry. Now for our function here, we're actually going to have symmetry only with respect to the polar axis, because of course this is a cosine function, so we know cosine functions are going to have symmetry with respect to the polar axis, but none of the other kinds of symmetry. And then, of course, we want to talk about where our maximum value for R is going to be. And that's absolute value of R. And we want to talk about where the zeros of our R values are going to be at. Okay, so again, let's do a table here. And I'm actually going to go from 0 to pi in this case. So let's see, if we use 0, our function is R equals 3 times cosine of 3 theta. Okay, so let's see, that would be 3 times cosine of 3 times 0, which is cosine of 0. And again, guys, cosine of 0 is going to be number 1. So that means 3 times 1 will give you a value of 3. Okay. If we wanted to do the next angle, which would be at pi over 6, it's 3 times cosine of 3 times pi over 6. Of course, 3 would go into 6 twice. So you would actually end up getting pi over 2 as your angle, and cosine of pi over 2 is actually going to be 0. So cosine of pi over 2 is 0, and of course 3 times 0 will end up giving you 0. And you can see that's how we would come up with our table. So go ahead and do this till you get all the way to pi. Okay, so we've got all our points over here, so let's go ahead and see where the zeros are going to be. So we have R equals 0 when our theta values are at pi over 6, pi halves, 5 pi over 6. So pi over 6, pi halves, and 5 pi over 6. Now let's see, our maximum value is at 3, negative 3, 3, negative 3. So that way we would say the absolute value of R equals 3 when theta equals, let's see, 0, pi over 3, 2 pi over 3, and the last one was at pi. Okay, so at 4 different angle measurements we have the maximum value, and at 3 different angle measurements we have our 0. So let's go ahead and see what this graph ends up looking like. So at 0 we are at 3, at pi over 6 we are at 0, pi over 3 is at negative 3, so pi over 3 at negative 3 will be right here. Pi halves is at 0, 2 pi over 3 is at 3, so 2 pi over 3 is at 3, 5 pi over 6 is at 0, and pi is at negative 3, which will bring us back to that first point. Okay, so we need to do these intermediate points over here. So let's see what this approximation for pi over 4 is. That's negative 3 square root of 2 divided by 2, and that's coming out to be approximately negative 2.1. So this guy would have to be positive 2.1. So let's see, pi over 4 is negative 2.1. Pi over 4 is negative, where are you? Negative 2.1. So somewhere over here. 3 pi over 4 is positive 2.1. So it might help to have some of these other points over here. So I'm going to use the concept of symmetry to help us out a little. Okay, so halfway between here, and you should have the same thing over here. So like I said, it might be helpful to come up with a few more points. Now we know this is a rose curve that's going to have 3 petals in it, so it's going to end up looking something like this. Okay. Okay, and then our third petal. Okay, there you go. At least you get a general idea of what this graph will end up looking like. So again, it's a rose curve that we have in here. Okay, so again, just follow those steps and you will get a decent graph for your function. Okay, let's see what we got. Okay, now let's do the last type of graph that we haven't seen, which is a Lemniscates. So this is where you have r squared equals 9 times sine of 2 theta. So that would end up looking like something like this third graph over here. Okay, so we have a Lemniscate. It's going to have symmetry with respect to the pole, and of course you will need to do the check for symmetry over here. Now from our table you can see that our maximum value is going to be right here at pi over 4. Our zeros are going to be at 0 and pi half, so you can kind of see those values right over here. Now here's the interesting part. So you can see how we have r square over here, right? So if we take r square of any number, it's always going to come out to be positive, because negative times negative will also give you a positive. So what that actually tells us is that this sine function cannot give you a negative answer. So the sine value cannot be negative because your equation will have no solution points with that, because like I said, if you take r squared, you are always going to have a positive on the left hand side. So if you have a positive on the left hand side, of course we have to have a positive on the right hand side, and so that's why our sine function cannot give us a negative answer. So this means we have to restrict the values of our theta for only those values where our sine function can either be 0 or it can be positive. So if you think about this, right here, our sine function is going to be positive from 0 all the way to pi, right? Because when you get into quadrants 3 and 4, our sine function is negative. So in quadrant 1 and quadrant 2, our sine function is positive. So that means if our sine function is positive for theta values which are between pi and 0, if we translate that to our function of 2 theta over here, right, and we go ahead and divide both sides by, or all 3 sides by 2, you end up getting 0 divided by 2 is 0, 2 theta divided by 2 is theta, and then pi divided by 2 is pi half. So that's actually how they come up with this boundaries on our theta value, which has to stay between 0 and pi halves. Or if you do coterminal angles, then you can actually go from 2 pi to 3 pi also. And so if you did 2 pi to 3 pi, hold on a second, so if your angle was between 2 pi and 3 pi, and again I go ahead and divide everything by 2, 2 divided by 2 will give me pi, 2 divided by 2 will give me theta in the middle, and then my last number will become 3 pi over 2. So that's how they're coming up with the second set of boundaries, but you can probably just stick with the first one, and if you need more points, then you can bring in the second limit over here. So again, looking at the type of function, we have the symmetry, the maximum points, the zeros, and then all of these values, you can see we can come up with this graph of our lemniscate, and this is kind of what it ends up looking like. So remember what I told you, it's going to be that infinity shape or that figure 8 kind of shape, which is what you get with a lemniscate. So let's see what our graph would end up looking like. We are given r squared equals 4 times cosine of 2 theta. So let's talk about the type of graph. Now, of course, since this is an r squared function equal to a squared cosine of theta or n theta over here, this is of course going to give us a lemniscate, okay? And then let's talk about symmetry. And this one will actually have symmetry with respect so it's going to be with respect to the line theta equals pi halves with respect to the polar axis and with respect to the pole. So it's actually going to exhibit all three types of symmetry here. Now let's see what we get for maximum value of absolute value of r, and where will our zeros be. Okay, so then we'll do a table here, but before we do a table, we need to kind of see what theta values am I allowed, right? Because again, you will notice we have r squared equals 4 times cosine of 2 theta. So again, since you have r squared on the left, which will always give you a positive answer, that means our cosine of 2 theta also has to be positive. So when cosine of 2 theta is going to be a negative number, less than 0, remember, this equation will have no solution points. So you won't be able to come up with any answers if you come up with cosine of 2 theta being a negative number. So that means we will restrict the values of our theta only where we can get a positive answer for cosine of 2 theta. So it can be 0 or it has to be greater than 0, okay? Just not less than 0. Okay, come on, buddy. Okay, so think about this. Cosine of theta, and maybe we'll write it like this. Okay, so think about where is cosine of theta going to be 0 or a positive number at. So if you go to your unit circle, you will see our cosine values are positive in the first quadrant and cosine is positive in the fourth quadrant, right? So cosine is going to be positive in the first and the fourth quadrant. So that means your theta has to be between 0 and pi halves. That's going to be our first quadrant, or it will be positive between 3 pi halves and of course 2 pi, which will be your angles for 4 quadrant. So now to translate this for cosine of 2 theta, we would have to do 0 less than equal to 2 theta less than equal to pi halves, or 3 pi halves over 2 less than equal to 2 theta less than equal to 2 pi, but then we would need to go ahead and divide everything by 2, which would be the same as multiplying by 1/2. So divide by 2, multiply by 1/2. So where you have divide by 2, 2 and 2 will cancel out, 2 and 2 will cancel out, and let's see, we will be left behind with 0 divided by 2 is 0, less than equal to 2 divided by 2, so that leaves us with theta, and then pi halves multiplied by 1 half will give you pi over 4, or let's see, 1 half multiplied by 3 pi halves will give us 3 pi over 4. Of course, 2 divided by 2 will leave us with theta, and then 2 divided by 2 will leave us with pi, and this is going to be when we want our cosine of 2 theta to be greater than or equal to 0. So these are actually the restrictions that we are looking at on our theta values. Okay, so when you create a table, you need to keep these values in mind. So let's see what that table will come out looking like. So we've got theta and r, and again I will go to from 0 to pi. So let's start with 0, and our function is given to us as r squared equals 4 times cosine of 2 theta. So that's r squared equals 4 times cosine of 2 times 0, which is 4 cosine of 0, and remember again, cosine of 0 is 1, so you get r squared equals 4, and of course we are only looking for a single r, right, which means we don't want to leave it as r squared. So when you take a square root on both sides, you get a positive and a negative root, so we'll end up getting r equals plus or minus 2. Okay, and then let's see for the next one at pi over 6 what happens. So you've got r squared equals 4 times cosine of 2, and then theta is pi over 6. 2 goes into 6 3 times, so we end up getting r squared equals 4 times cosine of pi over 3. Okay, sorry, my pen kind of keeps not working. Alright, so r squared equals 4 times cosine of pi over 3. And let's see, what is cosine of pi over 3? So pi over 3, cosine is going to be 1 half. And again, guys, that 2 will go into 4 twice. So we will end up getting r squared equals 2. Take a square root on both sides, plus or minus as our root, and you end up getting r equals plus or minus square root of 2. Okay, so go ahead and do the same calculation for all the way through pi, and let's see what kind of values we are coming up with for r. Okay, so remember our theta values can only go from 0 to pi over 4, so that would be the first 3 values in our table over here, and then you can pick it right back up from 3 pi over 4 to pi, which will give you the last 3 values of your theta. So just be very, very careful of what values you can use, because remember there are some values in here which we cannot use because they would end up giving us a negative value for the cosine function. So these are the only approved numbers you can use, and then of course anything in between of these two intervals. So you can see we have a maximum value here at plus or minus 2, and a maximum value here at plus and minus 4, and then we have zeros at pi over 4 and 0 at 3 pi over 4. So let's go ahead and write these guys down. So we have a maximum value of absolute value of r equals 2 when our theta is going to equal 0 and pi over here. When theta equals 0 and pi. And then let's see when is our r value equal to 0, when our angles were pi over 4 and 3 pi over 4. Okay, so let's go ahead and graph these functions over here. So at 0, we have positive and negative 2, so those would be those 2 points over here. Then at pi over 4, we have 0. At 3 pi over 4, we have 0. And then at pi, we again have plus and minus 2, so that would actually bring us back to these points, which means we're going to have to use the approximations for these guys right over here. So that's going to be plus or minus approximately 1.4. This would be approximately plus or minus 1.4. So that's going to be at pi over 6. So at pi over 6, we are at 1.4 and negative 1.4. And let's see, at 5 pi over 6, we are at 1.4 and negative 1.4. So something like this. And remember, this is a Lemniscates. You're going to make kind of that infinity type of a loop, which would end up looking something like this. Okay. Alrighty, and there you go. That's what your function will end up looking like. So remember, this is a, oh, wrong spelling. Lemniscates. Okay. Alrighty, so again, a lot of those calculations were similar. The only exception we had here is we had to figure out what theta values could we use here, because of the fact that your left hand side is going to be r squared, which means your cosine or sine function cannot be a negative number. Okay, so this is kind of what we do with this example over here. And this was the last example we had looked at. So we've seen Lemniscates, we have seen these rose curves over here, we've looked at these different descriptions, and then of course we've seen a whole bunch of Limocon examples over here. Okay? Alright guys, so look through this handout, look through the video, let me know if you have any questions, and we will answer those questions in class next time. So have a great day guys, be careful, be safe, and I will see you in class. Take care, bye-bye.